Hi, I hope you're all doing well. Today I'm presenting our approach to estimation and track control of cable-driven parallel robots using time-varying LQG. Cable-driven parallel robots, abbreviated CDPRs, use cables that are attached to an end effector on one end and driven by a motorized winch on the other end. By pulling on each cable, the end effector post can be controlled. Due to the fact that cables can only pull and not push, CDPRs require at least one more cable than degrees of freedom to be fully constrained, and are thus over-actuated. The resulting control challenges are actively studied by the cable robot community. For brevity, I'll focus on Mpc and Pid approaches. Mpc approaches, both linear and nonlinear, achieve good performance and robustness across the entire workspace, but are challenging to implement and have relatively low control frequencies. In contrast, Pid is very easy to implement and has very fast control frequencies, but can struggle near the edges of the workspace. We propose time-varying LQG, which we find experimentally to achieve more consistent performance across the workspace than a well-tuned dual-space feed-forward PID controller. At a high level, our approach consists of an offline stage and an online stage. In many circumstances, the desired trajectory is known in advance, so we can run trajectory optimization offline. Offline, we apply trajectory optimization to compute a nominal trajectory, compute the LQR and Kalman filter gains around the nominal trajectory, and combine them into a single controller to be run online. Because so much of the computation is done offline, our online controller is dead simple, requiring only 3 matrix vector multiplications and 3 vector additions per time step. As for the offline computations, I'm sure many of you already know how to perform trajectory optimization, compute LQR gains, and compute Kalman filter gains, but I'd like to take this as an opportunity to introduce you to an alternate way of computing these using a powerful tool that you may not be familiar with yet, which is called factor graphs. I'll show how factor graphs can easily and intuitively be used to solve all 3 of these problems. First, what are factor graphs? A factor graph encodes an optimization problem. On the top right is an example of a factor graph, where the x's and u's are variables to be optimized, and the 3 types of factors shown encode optimization objectives or constraints. The green, blue, and black factors encode the state tracking error, the control effort minimization, and the dynamics constraint equations respectively. As you can see, factor graphs are just a way to visualize the structure in an optimization problem. Using the insights gained by this visual representation, we can also leverage existing algorithms developed for factor graphs to perform very efficient optimization on sparse graphs. One such algorithm developed for factor graphs is called variable elimination, which is roughly equivalent to dynamic programming or sparse matrix factorization. In variable elimination, we eliminate one variable at a time until all the variables are eliminated. To eliminate a variable, say x3, we follow 3 steps. First, we collect all the factors connected to x3. Next, we solve for x3 in terms of x2 and u2. In this case, solving for x3 is trivial since the system dynamics immediately tell us x3 in terms of x2 and u2. We store this equation for x3 using the purple arrows, which are called a conditional, since x3 is conditioned on x2 and u2. Finally, we substitute the expression for x3 back into all the equations or objectives involving x3 and add the resulting objective as a new factor. This is just like an algebra class when you substitute a variable back into the system. Let's reflect on what we've just done. We had a system with 5 variables, then we solved for one of them, substituted it back in, and now we have a system of 4 variables. Here we sequentially eliminate one variable at a time until all the variables are eliminated. The conditional on the final variable eliminated will just be the optimal assignment for that variable, and we can forward substitute to obtain the optimal assignments for the rest of the variables. Foreshadowing, we can also see that the conditionals for all the u's look eerily similar to the LQR gain matrices. We can also note that this graph structure is common for optimal control problems where we have a chain of x's and u's. Variable elimination for this structure is linear time in the length of the trajectory. So now that we've seen the basic idea behind factor graphs and variable elimination, let's take a look at how we can use them for trajectory optimization. We solve the trajectory optimization problem using Levenberg-Marquardt, where the linear least squares problem in each iteration is solved in linear time using variable elimination. We choose to use the GTSAM software library, which has built-in routines for efficiently optimizing factor graphs using Levenberg-Marquardt with variable elimination. On the next slide, I will show what the factor graph looks like for our cable robot optimal control problem, which we feed into GTSAM. Although this factor graph may look big and scary, it's actually just the exact same kinematics and statics equations that have been standard in the cable robot literature for decades. So, for example, the yellow, orange, and red square factors represent the cable length equation, the wrench matrix equation, and the winch friction and inertia dynamics respectively. If we step back and look at the red squares, we see that if we group together some variables and factors, we actually have the same simple structure as the factor graphs shown in previous slides, with states x, controls u, and nonlinear dynamics updates. Reiterating, once we define the factor graph in GTSAM, we call optimize, and GTSAM returns the optimal trajectory x star and u star. Now that we have the nominal trajectory, let's take a look at how we can use factor graphs and variable elimination to compute the LQR gains. First, we linearize the problem around the nominal trajectory by calling graph.linearize in GTSAM. Then, we can run variable elimination from right to left the same way that we would do a backward Riccati pass. Recalling that variable elimination is just an algorithmic way to do dynamic programming, we can conclude that the conditionals on each of the delta u's directly read off the LQR gain matrices. Recapping, running variable elimination from right to left gives us the K matrix for each time step, which are the LQR gain matrices. Next, we show how to compute the Kalman gain matrices. Obtaining the time-varying Kalman gain matrices involves 4 steps. First, we convert the optimal control factor graph to an estimation factor graph by replacing the state objectives with measurement models, the control costs with noisy control input, and the deterministic dynamics with noisy dynamics. Then, we linearize the graph. Next, we compute the marginal covariances by successively adding one time step to the graph and eliminating the previous time step. For each time step, we do this once for the motion model prediction and a second time for the measurement update. With each, we record the resulting covariance after marginalizing to obtain 2 marginal covariances per time step. Finally, we use the 2 marginal covariances to compute the Kalman gains for each time step. Now that we have the nominal trajectory, the LQR gains, and the Kalman gains, we simply combine them into a standard time-varying LQG controller. The controller we run online looks like this, where we have our time-varying Kalman filter feeding the state estimate into our time-varying LQR controller. When we run our time-varying LQG controller on a 4-cable planar cable robot, we see that our controller achieves consistently good tracking accuracy throughout the workspace. We also compare the dual-space feed-forward PID controller from Gudafard's 2015 TRO paper as a baseline. We see that the performance near the center of the workspace is comparable, but the baseline has considerable overshoot near the edges of the workspace. In contrast, our controller maintains good tracking performance even near the edge of the workspace. In conclusion, we presented a time-varying LQG controller with more consistently accurate performance across the workspace, with a very fast online computations for high bandwidth control, and with easy offline computations using factor graphs. I'd like to finish off with the message that I think factor graphs can be powerful tools for representing and solving optimal control problems. Thank you for your attention, and I look forward to addressing any questions you may have during the Q&A period.